now. So without further ado, Jorge, we are all ears.
Thanks a lot, yeah. Thanks a lot for the wonderful introduction, and hi everyone, and also thanks everyone. It's nice to have people here online, like spending like 40-60 minutes of their time listening to me. So thanks everyone for coming. And what I'm going to present today is not a single work, but it's a combination of works under the same area. And they are, as Sia mentioned at the beginning, as the title of the talk says, they're about how we can use information flow analysis, and in particular taint analysis, to reason and to identify security and privacy properties on mobile and wearable device applications. Also, another thing that I would like to mention is that this work has not been only done by myself, but it's joint work with two of my students, Pallavi Sivakumaran and Marcos Tileria, and also with a collaborator, Guillermo Suarez. So I would like also to give the kudos to Pallavi and Marcos, because they did most of the work, and also they deserve all the praise for that. So what is this talk about? So this talk is about IoT devices and Android. Android in particular. When we talk about mobile, in most cases we talk about Android, because, well, as many of you probably already know, within the research community is the ecosystem that has been most studied, because it's the one that is probably easiest to study. So and in this talk, we're going to talk about these two categories of, let's say, devices, but we are going, I'm not going to analyze them separately. The idea is to analyze how they interact with each other, and what properties, what security properties do those interactions have in terms of, as I was saying, both security and privacy. And in order to do that, the idea is to use information flow analysis. So for the purpose of the talk, information flow analysis, or what we do when we are doing information flow analysis, is we are analyzing how information flows within a program. And when we are analyzing the information flow, basically, the idea is to analyze a variable or a value within a program and see where that value or the content of that variable ends up in the execution of the program. In order to do that, we can use two main techniques. One is basically dynamic analysis, where we would taint memory regions. We would execute the program and we would see how those taints propagate to other memory regions at runtime. Or we can use static analysis, which in most cases, not always, but in many cases, requires building a control flow graph of how the program executes, and looking at that control flow graph and traversing the graph, analyzing that graph basically to identify specific flows within the graph. So in the work that I'm presenting today, I'm mostly focusing on static analysis, and in particular in a category of information flow analysis, which we call taint analysis. So in these works, what we normally do is we are analyzing both IoT devices and Android applications, but the object of our analysis in many cases, well, actually most cases here, are Android applications. And this is because of several reasons. The first one is that dataset availability. Basically, it's very easy to access huge data sets of Android applications, and that makes research very much more accessible. Then a very interesting feature of Android applications is that in many cases, they encode the application of both the mobile app, but also the IoT device. And as we will see in the case of Wear OS, which is the Android version of operating system for wearable devices, they even encode the actual application that goes into the wearable device. It's obviously much cheaper and scalable analyzing apps than analyzing physical devices, because buying physical devices is expensive. And if you want to ask for money to do that, sometimes, when you want to do a big, large-scale analysis, it gets very, very expensive. And the other reason is because we also, and we will mention some of them, we have a lot of tools that have been developed by the research community that are widely accepted, and we even have benchmarks and a lot of widely accepted benchmarks. If we develop something, we can actually go and test against those benchmarks. So in taint analysis, what we normally do is we define what we call sources and sinks, and the idea is to see when use information flow analysis to check when those sources connect to the sinks. And whenever those things happen, we can probably infer some security and privacy properties. And what I'm going to present today are two different use cases. In one of them, we are going to use sources and sinks in Wear OS to identify privacy leaks, security properties of Android and Wear OS applications. And in the second case, we are going to use taint analysis, and we are going to define different sources and different sinks to identify how applications that deal with Bluetooth Low Energy cryptographically process data or not. And that will allow us also to say some or to identify some possible vulnerabilities that may occur in those applications. In most of these cases, whenever we do taint analysis, these are processes that are mostly automatic. And what happens is at the end, once we have done the automatic analysis, we sometimes check manually applications to actually identify and to verify that the issues that we identify are there, and to show also some use cases. So along the talk, I will also be talking about a couple of use cases. So we are analyzing, or we are looking at how Android interacts with Wear OS and how Android interacts with Bluetooth Low Energy. And before I go in detail into each of the cases, I thought that it would be interesting to show the difference between the interactions. So when a mobile application interacts with Wear OS watch, in most cases they are watches, what happens is the information that flows between the phone and the wearable will travel through either Bluetooth or Wi-Fi, but it won't go directly there. So when we are dealing with Wear OS, one of the key elements within Wear OS is this thing that we call Google Play services here. So applications won't directly connect between each other. They will connect through another application that runs in the application space that is called Google Play services. So what will happen is we will have intra-app communication between the app and Google Play services. Google Play services will take care of sending the information through Wi-Fi or Bluetooth, and that is out of the control of the developer and the user. And then the Wear OS will receive that information and will process that. It will go to the Google Play services app, and it will also go again into the other app on the other device. So this is important to note because of this intermediate process, it's not as straightforward to do analysis on this kind of intra-application and inter-device communications. In the case of Bluetooth Low Energy is actually very, very different. And that is what also makes it an interesting case. So in the case of Bluetooth Low Energy, what happens is that the applications access directly the Bluetooth process and the Bluetooth APIs within Android, and they communicate directly with the BLE stack of the corresponding device. This could be a wearable device, but it could also be like one of these smart locks, or one of these, even in some cases, the new keys that the car has, or it could be a smart meter. There are many different devices that communicate via Bluetooth Low Energy directly to the phone. So having made these two distinctions, I will now go and explain how we have used taint analysis to actually analyze these two different models. And in the first case, what I would like to present is a tool we developed, which is called Wearflow. And Wearflow performs information flow analysis that takes also into account the existence of these wearable applications. So it's not only between applications on the same device, but also between applications running on different devices, but within the same ecosystem of an Android user, let's say. So for those of you who don't have experience or don't know what Wear OS is basically kind of a stripped version of Android that there are a lot of changes, but the main change is that it's basically tailored to what we could call the grist experience. So basically the screens and everything are tailored to what you could see on one of these tiny screens that you have on your watch. The security model of Wear OS, it's very similar to Android. In fact, they share a lot of the code, and they even have like sandboxes, app isolation. There's also a permission system, but and this is one of the key differences. The permission system has one, some people could say minor, but it has huge effects, that which is that the permission authorization is independent from the mobile app. And that means that if I have two applications, one application and the corresponding companion, both of them have to request permissions on their own. So the permissions that the mobile application requests are not automatically granted to the companion app running on the watch, and vice versa. And we will see how this can open the room for different attacks. And in terms of network connectivity, well, Wear OS normally communicates with either the phone directly via Bluetooth Low Energy and Wi-Fi, or in some cases, Wear OS applications can connect directly to the internet. And this is done directly via Wi-Fi, or in some cases, it's done directly via the smartphone. But in that kind of distinction is transparent to both the developer and the user. You don't know when a Wear OS device is making a request that goes directly through the Wi-Fi network or through the phone and then to the internet. When we are talking about Wear OS, we normally have two kinds of apps. One of them are the standalone apps. These apps are the apps that don't require any kind of mobile companion, so you can basically download the app and interact with the app without any other requirement. These applications basically, or analyzing these applications, would be very, very similar to analyzing an Android application. So there is there are a few changes, but there is not a big deal of difference between analyzing a standalone application and an Android, a regular application. And then we have what we call companion apps. These are the apps that basically, whenever you download an app, I mean, in this example, I think the one shown is Facebook, but there are many others that have companion apps. Whenever you download the mobile application, you only get a download for the companion application onto your wearable device. And that, in a way, extends some of the functionalities of the wearable device, but at the same time has its own code and executes also on the watch. So it's not only acting as a screen or as another screen, but it's also running some processes and executing its own connections and so on. So when we have these companion apps, we have, in a way, we're extending the execution environment, not only to our phone, but also to these other Wear devices that we have. And that opens different new kinds of security threats or security risks. One of the, we listed three of them in this work, and the first one being permission redelegation. This is very similar to what would happen in permission redelegation between Android apps, but in this case, it happens between an app running on one device and an app running on another device. So the idea in this case is that one of the apps requests a set of permissions, and that app accesses those resources and sends the resources to the other app, without the other app requiring to request those permissions. And in a way, this what it achieves is it breaks the isolation model by inter-process communication. In this case, inter-device communication. Then, when we have permission redelegation, we can even have mobile or wearable data leaks. So when the sensitive data arrives to the other device, if that device leaks the data outside a server or whatever, we would have what we call a data leak. This is also very similar to what happens in Android-only scenarios. But in this case, we would have a communication between a mobile device and a wearable device in between. And another threat that we introduce in this work is what we call layer obfuscation. And this is kind of I would say, slightly or could be seen as a relatively far-fetched threat. But the idea of this kind of threat is that as developers, we try to prevent the analysis of our app by obfuscating the code and also sending information between both devices to make difficult the analysis of this information flow tools to understand if there are privacy leaks or not. This could be kind of something done on purpose by the developers to make more difficult the analysis of the application. So in order to analyze these three security threats, there is kind of a main or a summary problem that we need to solve, and it's the following. So we have a mobile application that is reading some kind of PII from a source. It's sending that PII through either Wi-Fi or Bluetooth to the companion app, and that companion app may send the PII outside the device. And in a way, this is an oversimplification, but in a way, we can summarize all the different threats that I showed as trying to solve this problem. And This problem, if we take information flow analysis, would be relatively easy to solve if we just add these different APIs here as respective sources and sinks, and we do the matching. However, there's a slight problem, as I mentioned in the beginning, that this process is not handled by the developer automatically. It's handled by a different process, with a different application, which is called Google Play Services. So what we need to do, or what a developer needs to do when they want to send information to the companion app or vice versa, is they basically send information to Google Play Services on a specific channel, and then the other application will receive that from Google Play Services. But there is no direct communication. So as a quick example, and this is a simplification of the code that you would see. So basically, on the first line, we identify the watch we want to connect to. On the second line, we just have like a simple text, hello. Third line, we would get some sensitive data, in this case, the location of the device. And here is when the interaction with the wearable and with the Google Play Services will start. So we would create a channel to send information. And in this channel, we would add two pieces of data. In the first one, we would send the location, which is the sensitive one with the tag sensitive. And in the second or sixth line, we would add a normal text, hello, with the tag greetings into the channel. And so far, the only thing that we've done is we've added things into a channel, but the communication, we haven't, as developers, we haven't forced that information to be sent to the device. And we do that with the final line, which is this one here. And as you can see in this line, what we are telling the program is send or map this channel to this node ID, which actually corresponds to a particular smartwatch. If we want to do information flow analysis of this, the problem we have is that because if we define this as a sink, we only have information about the channel. So, and basically the link between the geolocation here and the channel breaks through these APIs that we are not taking into account. So what we actually need to do in order to be able to cover this is we need to model all the different APIs that Google Play Services provide in order to be able to connect these two things and be able to say, whenever this happens, that actually the geolocation was sent through that channel. Okay, so how can we achieve this in like general broader terms? Well, so we have the two apps that we want to analyze. The first thing we do is we create this model of Google Play Services, and that entails identifying all the different APIs, creating new API calls that I'll show you an example in a few slides, and trying to translate this model, this Google Play Services set of APIs into something that can be added as real sources and sinks of these information flow analysis tools that we already have. Once we have this model, what we do is we take the apps and we instrument those apps, replacing some of these calls by the calls in our model. Once we have done that, we can actually run these applications through the usual time tracking tools that we have. Once we have run those time tracking tools, we can actually perform the matching between the sources and sinks of each of the apps to see if there's actually any path that goes from one device to the other. And this is the simplified version. This is a bit of a more complex version. Just to give you an idea, we do there's a process of preprocessing, deobfuscation, and so on. The instrumentation process is done with Soot. And once we have done the instrumentation part with Soot, we have code that can be analyzed by tools like FlowDroid. So we just pass the new apps that we have generated to FlowDroid. So, and then of course, after FlowDroid, we do the matching analysis, and that gives us the flows that go from one device to the other. So, well, here are the reference. So how this actually works in terms of an example. So this is the example that we had in the previous slides. So the first thing that we do when we are instrumenting is we identify the APIs that are within our model. In this particular case, the API that triggers the transfer of information between one device and the other is this call, where API.synchronize data, node ID, and channel ID. Because we know that this API is based on channels because our model, the next step is to identify the channel creation. When we need to go backwards on the code, so we do backwards analysis to identify where the particular channel that is being sent through that synchronized data call is defined. Once we identify the channel, we now need to go forward to identify the data calls or the calls that put data into the channel. Once we do that, the next thing is we evaluate the context. So we extract all these strings because we will need them to generate our calls. And once we have generated these strings, we use this model that we had to generate these new custom API calls. And this is one of the examples. And once we have generated the custom API calls, we just replace the original code with the where API with these calls. And if you look at these two new lines of code, in the original code, which is this one, this single line of code didn't allow us to do the information flow analysis because we were missing the connection between channel and location, basically. But in these ones, we now have the location in the same call as the sync. So the only thing that we need to do now is tell Wearflow that this new kind of API call is a sync. And Wearflow will take care on its own. Sorry, Wearflow, FlowDroid will take care of identifying the sync and with the automatic inference that we've made for them. So in a way, we are basically transforming a few API calls in such a way that we can help the current information flow analysis tools to make their job better. So we did, we developed a workflow for all the set of APIs that Wear OS uses. And we did an evaluation where we basically created what we call Wearbench, which are 15 apps with a few information flows. We executed Wearflow. We found, there are false positives, and I will talk about the limitations at the end of the talk. And we saw that adding Wearflow to the whole execution added only around 11% of overhead compared to running only FlowDroid. So we perform a large-scale analysis over 3,000 pair of wearable APKs. These were obtained from RHUL. Overall, while we had 3,000 pair of APKs, we only had 220 unique package names. This means like a unique different applications. Overall, the analysis was around 115 hours with an average of 3.1 minutes. And I'm going to present a couple of results. So the first one has to do with the different flows that we saw from one app to the other, from one of the devices to the other. So if you see here, these kind of green flows are flows that go from mobile, and the more like purple ones are the ones that originate or end in a wearable device. So we can see that both of there are two main APIs that can be used, and both are equally used. Interestingly, in most cases, what we saw were flows from mobile phones to wearable devices instead of the other way around. And we didn't identify huge leaks. This is kind of good news, but then we'll see some examples of, actually one example of uses that wasn't as good. So if you check the list of things here, there are very fewer cases that are of interest. So for example, we have HTTP connections here, and there is an open URL here. So a few things that happen, but in many cases, things were going into the logs. Now with new versions of Android, this is not easily accessible by other applications, but still probably not a very good developer practice. And in some cases, things going into broadcast, which probably is also not a good idea, or into shared preferences files. And when looking into specific details, I'm going to present a use case of applications that we identified. This is a watch face that you can find on the apps on the Google Play Store. And what we saw in this case is that this had 2 applications, okay? The mobile application would request permissions to access phone calls and messages, but the wearable application wouldn't. And what would happen is that the mobile application basically took both the missed phone calls and the SMS messages, and that were read and pass those messages. Well, I haven't actually checked if it still does that, but it passes those messages via a send message called of message client into the wearable application to probably to show them to the user, but also saves them into a file. So while some people may not see this as a huge threat, and I myself don't see this as a huge threat, we have to be realistic here, but this actually goes against the Android developer guidelines, because the wearable application should also ask for those permissions if it's accessing that data, so the user is aware of what is accessing what, because also the wearable application can communicate to the internet as well. Okay, so now that we've seen the case of Wearable, well, actually, there's a question here from Charles. So Charles is asking if this could also be used for things like phone, mail, and text interception. And the answer is yes, but there is, so one of the restrictions that Android imposes on Wear OS applications is that they can only connect with applications that have been signed with the same certificate. So you basically, what you are doing is you are splitting your app into 2 different devices, and you can communicate things to the other device as well. So you could do that. Yes, I mean, for example, the developers of this application could do that maliciously, but we haven't seen that happening. What we have seen in most cases are developers doing things, and actually in the Bluetooth Low Energy case that also now we'll see that as well, developers doing things the way they shouldn't, because they are not aware of the security and privacy implications that this happens. This is not very new, I know, but still it proves that things are still being done in the wrong way, and things could still be improved.
So your research assumes well-meaning developers, and that would require bad developers, as it were.
Yeah, I mean,
Yes.
in some cases, and I'll talk about this in the Bluetooth Low Energy scenario. In some cases, we've seen things that could be seen as malware, but when you are actually looking in detail, you see that they did things wrong. It wasn't maliciously. So they basically, for example, copied and pasted code from GitHub, and that included things that shouldn't include. But I'll show an example later on. So now, so in this first case of Wear OS, what we did is we looked for security properties in the apps themselves, okay, and see if there were any kind of privacy leaks between the apps. Now, and what I would like to do, well, quickly reminder, so this was the case of Wear OS. Analyzing Bluetooth Low Energy devices is much simpler because we only have to analyze actually the Android side of things. And so the question is, so in this case, we are analyzing something completely different, and we are using taint flow analysis to find a completely different, or to identify a completely different issue. And why do we do this? Well, so before that, I will quickly explain a possible attack that can happen, and I will then explain how to identify apps that are susceptible to that attack. So when we are accessing information in any of the devices that we have connected with Bluetooth, something like this happens. The phone makes a read request to read something on the device, and the device replies with the data. We could do this for, as I was saying, smart locks, glucose monitors, cars, smart meters, and so on. But this is what we normally see. So, but the first time we do that, and if the data is properly protected, what would happen is that when the device makes a request, when the Android device makes a request, the Bluetooth device will return an error with insufficient authentication. Then, you won't see that error as a user. What you will see is a pairing request, and you'll compare the numbers, you'll say pair, and everything will happen under an encrypted link from that moment onwards. So the device will make the request again, and it will receive a response. But the problem here, and this is a problem that Android has, is that what happens if another application tries to access a device, like, for example, in this case, a glucose meter that has already been paired? Well, what would happen as of today is that the application would be able to access that data independently of who initiated the encryption between the Android device and the Bluetooth Low Energy. This is what we call the collocated attacks. And this happens because Bluetooth permissions in Android are categorized as normal. And because they are categorized as normal, they are only checked during installation time. So there's no user prompt at runtime. And applications with Bluetooth permissions, so any application that was installed with Bluetooth permission, will be automatically able to access all previously paired BLE devices without any kind of user interaction. This is similar to an attack that already existed for Bluetooth Classic, but the problem is that with the case of Bluetooth Low Energy, it even requires less permissions to execute. We notified about this issue well. They acknowledged it as a moderate issue, and they mentioned that they were doing what is within the quotes, basically documentation revisions regarding the issue, so they would make clear that this could happen. And they didn't. They were still discussing these other possible remediation options. As far as I'm aware, they haven't implemented any yet. And this is a message. So if you go today to the Bluetooth Low Energy developer website of Android, this is a warning you will see that says when a user pairs their device with another device using BLE, data that is communicating between two devices is accessible to all apps on the user device. For this reason, if your app captures sensitive data, as many Bluetooth devices could, you should implement app layer security to protect the privacy of that data. So the remediation that is proposed by Google about this issue is to use application layer security. So what we did is, okay, can we try to identify if applications have some kind of app layer security? And this is what we actually did with thing tracking. So the idea behind this is that if an application is using app layer security, they will probably have some kind of cryptography involved on it. So whenever they are going to send data through BLE, they will encrypt the data. And whenever they are receiving data, they will decrypt the data. And in a similar way, they will either generate hashes and HMACs or try to verify hashes and HMACs. So this basically says that if I want to instantiate this problem as a taint analysis problem, this is what I will need to do. So I will split the problem in two taint analysis problems, one for writing, another one from reading. And what I will do is that whenever I'm sending data to a BLE device, this would be with, by the way, with the, if I'm sending data, this would be with the set value. The BLE, so what I need to do is I need to check that the crypto methods are tainting data that is being written. Whenever I'm reading, so in this case, this would be basically the source, and this would be the sinks. And when I'm getting values or when I'm reading data from Bluetooth Low Energy, what I need to look is, okay, so this would be the source. So the Bluetooth reading methods will be the source in this taint analysis problem. And I need to check if these sources are connected to cryptographic libraries to see if there's any kind of decryption of that data. So in that case, the cryptographic libraries will be the sinks. So basically, yeah, this is kind of, so what we did is we implemented these two taint analysis problems in a tool called BLE Crypt Tracer with the sources and sinks as are written on the slides for both reads and writes. And in this particular case, we didn't use FlowDroid because this was a very narrow use case. And we did a few experiments and we saw that analyzing the number of apps we wanted to analyze with FlowDroid would take a lot of time. So what we did is we developed a very specific implementation of flow analysis problem. And because we did this, we also created an evaluation benchmark. And what we did is we took all the Droid Vents benchmark, which is a benchmark for Android applications. We created a VLE version of that with almost 200 APKs. We executed, it's basically the same, but instead of having API calls to sensitive APIs and other things, what we had were BLE libraries and crypto libraries. we had very similar results to what a Floatroid and Android would get, but in contrast, our analysis time was much shorter. So we thought that, and we still think that it was worth the effort to do this specific implementation. And what we did is we did a large-scale analysis of almost 20 Bluetooth low energy APKs with 11,000 unique package names, which basically means that 11,000 different applications. We executed our taint analysis problem for both reads and writes. And I'm going to present a few bits of data. It's not all that we got, but I think it says a lot. So, and these are the APKs with cryptographically processed BLE data, both for reads and writes, for different categories on Google Play. So there are a lot of interesting things to unpack here. One of them is that the medical, in this case, the smaller the bar, the worse it is. So in this case, as you can see, the medical devices or devices that are considered, or applications that are considered under medical, are the ones that have less protection. And that means that data that was sent or received was not processed cryptographically in more than 40% or 60%, sorry, of the applications we analyzed. We believe that this is because they use standard versions of a few like heart rate and things like that are transmitted without being encrypted actually, which is a problem. And you see surprising results like travel and local, in which 90% of the apps have some kind of cryptographically processed data. And we found that this was because most of them implemented a beacon library that has proper cryptographic protections to handle beacons. So that they were doing well because they were implementing libraries that were doing well. We did more analysis on applications that had crypto, and this was executed with CogniCrypt, which is a tool that I think was developed by the group of Boren in Germany. And well, we found a few issues. And the interesting thing about this is that, I mean, some of these issues were, I'm not sure if using ECB in this particular case is like a huge threat, because the kind of data that is transmitted is very small. But these kind of issues show how implementing your own cryptography doesn't always end up in good solutions, and why it's probably not the best idea to leave to developers deploying and developing their own app layer security methods, because they will do things wrong. But that is probably another discussion. Sorry?
No.
So we also did some additional analysis on some applications, and we were even able to, for example, update the firmware of devices through other applications. So the original or the official application would be installed on the device, and another application that we created would wake up the BLE device and would rewrite the firmware of the BLE device, because the firmware update mechanism didn't have any kind of security protection. So this kind of attack can lead to, not only reading or writing information from the device, but also even modifying the firmware of some devices. So as a kind of summary, well, a few limitations. Taint analysis is not the perfect method, of course. Probably there's not perfect method, and it has a few important limitations that should be mentioned. The first one is that the accuracy of what we can achieve depends on the complexity of the model. And in fact, the latest point, the last point of the slide, is also important, that if there's a new software update that introduces new APIs, changes how Google Play services works from the inside, and so on, this will break the model and will automatically make the analysis less accurate. So it basically requires to keep an eye on how the system is developing to constantly update the model. It would be actually very interesting to be able to develop automatic solutions that analyze these software updates and probably develop new upgrades for these models. While it's probably much faster than doing dynamic analysis and much cheaper, also depending on the complexity of the applications, it can also be very time consuming. And in some cases, it can be even not a non-solvable problem for some applications. So in fact, I don't remember the numbers now, but in both analyses, there were a few apps that where our timer ran out. So, and we couldn't obtain results for them. In a similar way, obfuscation is difficult to address. So while in both cases we implemented methods to identify different kind of obfuscation mechanisms, we are not able to fix and to identify all kinds of obfuscation and to revert all kinds of obfuscation. So taint analysis is generally weak, I would say, against obfuscation. And of course, in these two particular cases, and probably in many that use Floatroid and similar tools, dynamic payloads that are downloaded and during runtime are not going to be able to download unless you do some kind of pre-loading where you try to download all the code. And native code in the case of Android, which if you're not aware, in Android you can do things in Java/Kotlin, or you can try to do things in directly native code. And these tools normally, there are tools that try to connect native code with Java, but you have to also extend these models for these native tools. So they are more difficult to analyze via static analysis. So in summary, I think these two works show that taint analysis techniques can be used to determine security and privacy properties of mobile and IoT devices and interactions with those IoT devices. And in this particular case, with wearable devices. Using apps as an analysis point is actually an efficient venue to perform large-scale measurements of device ecosystems, so we don't have to buy them. And the overall results that we obtain in both cases point that both BLE and Wear OS applications exhibit a lot of security and privacy issues, not at the single levels, but at market scale. So there are a lot of things that need to be fixed. And that is all. Thank you very much, everyone. And again, I would like to thank my co-authors, Pallavi, Marcos, and Guillermo, with a special thanks to Pallavi and Marcos, because as PhD students, they did most of the work. So again, they should deserve the praise. So thank you very much. And if you have any questions, I would be very glad to answer them. I see another question here. So 11,000 watt, if this is referring to BLE case, this should be here. So so we had around almost 20,000 APKs, but only 11 of them were unique packages. So basically there were around 7,000 that were updates of apps that we already had. Okay. And I think it's important to mention this because it's almost double. So, and it's, in most cases, we saw that the issues were the same in all versions, but the size of the ecosystem can change a lot depending on how you analyze it. So in real terms, there were around 11,000 unique apps. But in reality, there are many more. Because the way we obtain the data, this is actually a bit difficult. So when you are obtaining the data set from RHUL, you don't know if the application has Bluetooth capabilities. You have to download the app, check, and check the next one. So what we did is we downloaded almost 5 million APKs and check each of those. And because you have apps being added every day, it's actually very difficult to keep up. And is there a paper with a percentage of APIs with a problem diagram? Could you describe what you mean by a problem diagram?
Sorry, your last image, the one with the results, is great, but it's not in the paper with the other images. I just wondered if it was published anywhere.
You mean this one that I'm showing right now?
Yes, that one. Yes.
Yeah, this one is a simplification. So in the paper, we have more, we have, I think, the same image, but with more columns using all the categories on Google Play. This is a sub-selection of categories that we found interesting for the presentation.
Okay, this is the Usenix paper.
If I am correct, let me check if I am correct in the paper. There was like a figure 7, I think. And what we did is because there were a lot of categories that probably were not very useful to show, and I think there are around 15 categories, and 15 categories on a slide were too much. We decided to compress everything. I mean, to leave out a few, basically.
Could you put a link to that paper? Please, could you put a link to that paper somewhere? I can't find that one. Only use Usenix.
Yeah, let me. So.
Or a ref or something.
So this is the link to the. It's on the chat right now, I think. That's the link to the Usenix paper, and on that paper, figure 7 includes. This figure is a subset of figure 7. If it only in figure 7 we have 1, 2, 3, 4, 5. Yeah, it's around 15 to 20. I don't remember the number, but it's between 15 and 20 categories. And for presentation purposes, it's too crowded, so we took a few out.
Great, thank you.
Thanks, Jorge. You went immediately to the questions, so we didn't get a chance to thank you for the presentation.
Oh.
We have another. So on behalf of everyone, I'm sure that everyone wants to thank you for your presentation. So I clap on behalf of everyone, and then we have another question, another hand up, actually immediately from Soteris.
Hi, Jorge. Very interesting presentation, and thank you for your talk. I have 2 questions. The first one is, can we access the tool? Is this available? And sorry if I missed that.
Yeah, the tools are available. I have like these extra slides always. So all tools are on either GitHub or GitLab. Actually, we need to move the first one to GitLab, but BLE Crypt Tracer is available. GitHub, it's Python. Wearable, it's a combination of Python, but you also need access to, of course, FlowDroid. So you'll need Java and download FlowDroid and so on. It includes also like updated sources and things for both of them. And if both BLE Crypt Tracer has a direct link to the benchmark that we use, and for Wearable, we decided to have a benchmark on our different repositories. So if you want the benchmark to do some tests, you can go to the specific GitLab page for the benchmark.
Great, thanks. My second question.
The thing that we cannot provide, the thing that we cannot provide are the apps. I think we have the hashes of the apps, but we cannot upload the apps.
Sure, that's fine. Great, thanks for sharing that. My second question is with respect to mitigation mechanisms. I was wondering, what are your thoughts in terms of protecting against escalation attacks, either on BLE or across companion apps? I'm not a huge fan either of application level security, especially in the context of the Android ecosystem. We've seen a lot of things happening throughout the years. And we have proposed in the past something that is based on SE-Linux that will allow you to protect access to BLE devices that pair with the phone. And this is with respect to the problem. I think you have one citation with the BLE Classic. That's the problem we found in the past. So we have a solution of that based on the Android operating system, and adapting the SE-Linux policies and extending the SE-Linux policies to protect access to that. So I was wondering, what is your approach, or what are your thoughts in terms of mitigation mechanisms?
So within the group, we've had a lot of discussions about this. I think it's an important debate, because we identified like 3 different stakeholders. One of them is Android in this case, because for the Bluetooth case, the issue that you mentioned also about Bluetooth Classic happens because how Android has implemented this. It doesn't happen exactly the same way with iOS. The other stakeholder is probably the Bluetooth special interest group, the standardization body. They didn't thought when they created the BLE specification, they didn't thought about that BLE would be implemented in like multi-app application devices. And the third stakeholder are the developers. So we've already measured how the developers are doing. So we are, let's say, removing them from the equation because we see that they are not doing very well. And the two stakeholders that we have left are the Bluetooth Special Interest Group and Google. We told Google what we think they should do, which is basically it's as simple as giving, and actually we submitted a paper to a conference recently with this proposal, that they need, it's basically making the users aware when an application is trying to access a Bluetooth device. So because at the moment, the channel between the encrypted channel is between the BLE device and all the applications. So what Android should do is probably have one access control mechanism to check. And you could implement that, for example, with this SE Linux, or you could implement this in all different ways. So we think they should do that, but in order to force them to do that, we also think that it would be good for the Bluetooth Special Interest Group to acknowledge that Bluetooth is an application level protocol, and they sell it as an application level protocol. And if you sell a protocol as an application level protocol, you should include mechanisms for it to behave as an application level protocol. So if the Bluetooth Special Interest Group proposes changes, then all the manufacturers need to implement those changes in a way. So that would that would cascade down all the changes because they are the ones actually deciding the standard. However, Google and other companies are part of the special interest group. So at the same time, it's kind of like a egg and chicken kind of.
Yeah, no, I see what you're saying. Yeah, I guess the issue with changing the Bluetooth stack is you can add an authentication layer, but I guess that's going to be another API that application developers might choose to use or not. And in terms of ease of utility, they might just skip it again. So I'll always vote for the operating system to take things into their own hands. And
I agree. I agree with you in this case. They should be the operating system dealing with this.
Yeah, so maybe I'll share in the chat what we've done on this with the Bluetooth Classic. You might find it interesting, and I look forward. If you have an archived version of the work that you've submitted with your proposal for the solution, I would love to give that a read. On where that comes out, maybe you can share that in the group.
I'll send you that privately if you're okay.
Sure, that's excellent. Thank you very much, Jorge.
Excellent, thank you.
Thank you. There's another question from RHUL.
Hi, Sia. Hi, Jorge. I think we are running out of time, but I will ask my question quickly. It's an excellent presentation, Jorge, and glad to hear Google kind of recognize your work. Is amazing. My quick question is, you mentioned that in order to capture the data between the mobile device and the wearable device, you are orchestrating a Google Play. I think you kind of build a kind of a performing man in the middle attack between the device. Yeah.
It's not exactly that. I mean, what we do is we modify the code of the app so it's more explicit, let's say, the kind of communication that happens.
So that since you are modifying, you can have your own certificate. You don't need to worry about Google Play service certificates, right? So
the modifications, actually that's a very good question. So the modifications that we make to the app are only for analysis purposes. We don't execute them afterwards. Actually, I mean, I think they should execute. I mean, we haven't tested it, but they should probably execute because we create like modified versions of the libraries and so on. But the analysis is only so the modification is only made for analysis purposes. So basically modify the code and then pass the modified code to another tool that we know can handle that code. But it's a good point. We haven't, we should check.
Thanks a lot. Thanks.
Thanks a lot, RHUL, for the question.